So for this video, we're going to talk about the second derivative in concavity. So first, let's recall about the first derivative. So let's recall for if we take a function y equals f of x, the value f prime of a, this is the slope of the tangent line at x equals a. So if we think about what this means geometrically, we can look at it in terms of the slope being positive or negative and what that tells us about the function. So if the slope is positive, my function looks like this, then the slope is going to be positive. So this line here, the tangent line, has a positive slope. So in this case, we see that the function has to be increasing for the slope to be positive. So f is increasing at x equals a is equivalent to the derivative being positive. So we can measure increasing based upon the sign of the derivative. And similarly, if the derivative is negative, put some labels on these axes. If our derivative is negative, like this, notice the slope of this line is negative. In this case, our function is decreasing. So that's how our first derivative can tell us something about the geometry of our function. We want a similar thing for the second derivative. So first, let's go ahead and recall what the second derivative is. So this is just the derivative of the derivative. So that means we just use the formula for the derivative, but we put in the function, the derivative function, instead of the regular function. So we might write this as f double prime. Maybe we'll just put it for the function instead of at a particular value. So it's going to look the same when we first started, but now since we're taking the derivative of the derivative, we want to use the derivative function here rather than the original function. Okay, so notice we have the derivative function there. So we're taking the derivative of the derivative, and we might also write this as in this notation as well. So let's go ahead and calculate an example of this. Okay, so suppose we have the position function of some object, and we're going to give this by this function s of t, which is going to be 10 plus 15t minus 4.9t squared. Now recall, we know that the velocity function is the derivative of the position function. We also have that the acceleration function is the derivative of the velocity, which means it's the second derivative of the position function. So let's go ahead and calculate the velocity and the acceleration. So the velocity is the derivative of the position. So let's use our formula here. So we just do exactly what we've been doing so far, and we plug this into the actual function, and then we're going to do some algebra. Okay, so all we've done here is we've just plugged into the formula for the position. And now we're just going to simplify things by foiling things out, and then we'll get some cancellation. So if we do that, so multiply everything out here. So let's maybe just write this as 15t plus 15h minus 4.9. Then we get t squared plus 2th plus h squared minus 10 minus 15t plus 4.9t squared all over h. And then we can see we're going to get some cancellation here. So what I'm going to be left with is the 10 and the 15t are going to cancel, and the 4.9t squared will cancel. So I will still have my 15h minus 4. Well, when I distribute it through, I'm going to get minus 9.8th minus 4.9h squared all over h. Now, if I divide the h through, I get 15 minus 9.8t minus 4.9h. And so we take that limit, the h goes away, and this just gives me 15 minus 9.8t. So my velocity function, just to recap, is 15 minus 9.8t. And so now to calculate the acceleration, we take the derivative of the derivative. So this is s double prime of t, which is just the derivative of the velocity. Okay, so just apply the same formula, but now apply it to the velocity function. So if I plug this in, I'm going to get a 15 minus 9.8, replace the t with t plus h, and then 15 minus 9.8t all over h. And if we FOIL out and we cancel, we're going to get the limit as h goes to 0, and I'm going to get minus 9.8h over h. So this is just minus 9.8. So my acceleration function, just to recap, is just the constant minus 9.8. And we didn't give units, so we will leave units off, but usually this is in meters per second squared. So now that we know how to calculate this, we want to go ahead and follow through on what we said and figure out what does this mean in terms of the geometry of the function. So we're going to take the thing we said above about the derivative of a function, but now we're going to apply that to the derivative function itself. So we want to apply the material we started with. So we're going to use f prime instead of f. So then we'll be talking about the second derivative. So what that would mean then, if we rewrite those things, we would say f prime is increasing at x equals a is equivalent to f double prime of a being bigger than 0. So we've just replaced everything by taking the function, replacing it with the derivative, and then using the derivative of that function, which is the second derivative. And we get the same statement for when the derivative is decreasing, is equivalent to f double prime of a being less than 0. So we saw in the flip class video what these things mean. So if f prime is increasing, that means the slopes of the tangent lines are getting bigger. So for example, let's see a picture of when that could be happening. So for instance, if I have a graph that looks like this, notice my tangent lines as I move to the right, these slopes here, these are positive and they're getting steeper. So f prime is increasing here because the slopes of the tangent lines are getting bigger. And we saw another example of this in the flip class video, kind of going in the other direction. So that was when the function was increasing. We could also have the function decreasing like this. And now notice the slopes of the tangent lines are negative now. And so as you go down, they're increasing because they're negative and getting closer to 0. So this also has f prime is increasing. So we saw what we said was a graph that satisfies either of these conditions is called concave up. So a typical concave up graph looks something like this. It could be either side of it, both sides, it doesn't matter. But you can see this is exactly the type of pictures we drew above. So this is called concave up. And so this happens when the second derivative is positive. So one way to remember this, if you don't want to go through the logic of this each time, is so concave up is equivalent to f double prime being positive, which we can think of as a plus. And then we can draw a little smiley face with stars in their eyes because they're happy. And so that's concave up. You get the smiley, the smile is the concave up part. And you get the positives because the person's happy. And now we can do the same idea for concave down. So if f double prime is negative, we went through this in the flip class video, so I'm not going to go through all of it here, but concave down looks something like this. So the trick for remembering in this case, so concave down is equivalent to f double prime being negative. So write a negative. And we can think of, in this case, a frowny face. And the person has their eyes closed because they're sad. So that's our little trick for remembering the concave up and concave down and what it means in terms of the sign of the second derivative. Okay, so let's look at another example. Let's look at another example now. So let's recall we saw before the logistic equation. So we gave a formula for this before, but for what we're doing here, we don't really care about the formula. All we care about is the graph. So we saw the graph. So this is our logistic curve here, and we had some value up here, L, that the population is going towards. We had our P0 down here where it started, and then we have this value here, T0. And we gave this T0 before, but we didn't really say much about what this is. So let's look at the graph and the geometry a bit for this. So we know that this is always increasing. So if it's always increasing, that means its derivative is always positive. Now we can look at the graph and we can see up until t0 it's concave up, and then after that it's concave down. So for t less than t0, the graph is concave up. So the second derivative is positive. And for t bigger than t0, the graph is concave down. So p double prime of t is less than 0. So notice what this is telling us. For up until t0, we have that the population is growing, but it's growing faster and faster, as you can see by the shape of the graph. So for t less than t0, okay, so it's increasing at an increasing rate. So as we get closer and closer to t0, the population is growing faster and faster. Now after t0, it's still growing, but it's growing at a slower rate. It's starting to level off. So for t bigger than t0, the population is growing, but at a decreasing rate. In other words, it is leveling off. Now, if we look at the value at t0, we saw that before t0, the second derivative is positive, and after t0, it's negative. So that means it must go through 0 at t0. Okay, and so this is a point, this is where it changes concavity. So this is called an inflection point, a place where it changes concavity. It's called an inflection point. And one other thing we saw before, but let's just refresh our memory on it. We saw that the limit is t goes to infinity of p of t is equal to L. This is how we first introduced the logistic equation, was when we looked at limits. So this L is called the carrying capacity of the environment. So if you take some biology, you'll likely see this. Okay, let's look at another example. Okay, so let's put a graph here. So I want that to be. Okay, so it doesn't want to let me erase this. Let's see if we go this way. There we go. Okay, let's put some x values on here now. Okay, so these are our values now. And now let's ask for some questions for this. So which values are the following true? Or could the following be true? That's the same thing. Let's just say for the first one, let's say f of x is less than 0. So which values for that? Well, this just means below the x-axis, so this would be x4 and x5. Now let's ask, what about where the derivative is less than 0? So this should be where the function is decreasing. So it's decreasing at x3, and it's still decreasing at x4, and everywhere else it's increasing. We could also phrase this as where f is decreasing. So phrasing this in terms of the function instead of the derivative, but these are the same value. That's the same thing as part B. And then we can ask, where is f prime decreasing? Well, f prime is decreasing. Remember, this is when f double prime is less than 0, which is the same thing as concave down. So concave down should be the point here. Looks like here's concave down, here's concave down. X1 looks like concave up, X4 and X5 look like concave up. So this looks like X2 and X3. So notice that x2, the function itself is increasing. That doesn't matter for concave down. We're looking for the second derivative being negative, not the first derivative. Okay, let's try a couple more examples. Okay, so our P of t is going to be the price of some stock of a corporation at time t. So let's interpret a couple of statements about the stocks. Okay, so I'm going to give a couple of statements, and we're going to determine what they tell us about the first and the second derivative. So for the first statement, let's go with the price of the stock is rising faster and faster. Well, the first thing to think of here is the rising part. That tells us increasing. So P prime is bigger than 0 because it's increasing. And then the part here where it says faster and faster, that's telling us that the increase is getting bigger and bigger. So that tells me the second derivative is bigger than 0. This is because the faster and faster. So let's try one more statement. Okay, so the price of the stock is close to bottoming out. Well, bottoming out means it's decreasing. So you can think of it looking like this. And we can also see concave up because it's getting flatter. It's not decreasing and decreasing faster and faster. So this should tell me decreasing. But then the second derivative is still positive because it's concave up. So this kind of gives us a real world, like if you're told something in the news about stock price, you can tell what's going on in terms of the function, what the function of the price of that stock actually looks like. Let's try one more example before we close out this section. So let's graph the second derivative. Of the function pictured. So here we'll graph our function. So it goes down. So if we want the second derivative, what we really need to figure out are where are our inflection points. So we can see right here, it looks like it's switching from concave up to concave down. And then somewhere like here, it's switching from concave up or concave down to concave up. So these are our inflection points. And so what do our inflection points indicate? Well, those are where the second derivative is equal to 0 because we're changing concavity there. And so we're concave up means we're positive. So in this part over here, we're positive, negative, and then positive again. So what we're looking at is we're positive here, and then we're negative for a little bit, and then we're positive again. So this is what our second derivative would look like.